Welcome to today's Explainer. We are diving into some seriously fascinating new research on how to actually master enterprise RAG optimization. We're talking about aggressively cutting your LLM token costs and completely eliminating retrieval noise. So, if you're an AI engineer, an MLOps architect, or a data scientist building enterprise search engines, buckle up. We're moving way beyond the basics today to see how leading practitioners are fundamentally upgrading their pipelines. Let's just start by questioning the standard practices we all lean on. It's kind of a hard truth in production AI, right? Every single irrelevant token your LLM has to read inside its context window is literally just draining your budget. Improving retrieval precision isn't just about getting better answers anymore. It's a strict economic mandate, because honestly, every single document you don't send to the LLM saves you money. Here's our quick roadmap for the explainer today. 1. Beyond naive RAG metrics. 2. The semantic fragmentation problem. 3. Token-level IOU math. 4. The chunker model performance matrix. 5. Domain-dependent variations. And finally, 6. Optimizing throughput and cost. All right, let's jump right into section 1, beyond naive RAG metrics and looking at the token-level paradigm. So traditional information retrieval metrics, like coarse top-K accuracy, treat chunks as simple binary hits or misses. They just ask, did a relevant document appear in the top 5? Well, that completely overlooks a critical reality. The LMM doesn't care about a document's position on a ranking list. It evaluates and charges you for every single token you feed it. That's exactly why we absolutely must shift to a token-level evaluation paradigm. We need a metric that actively and directly penalizes retrieval noise. Which brings us perfectly to section 2, the semantic fragmentation problem, also known as the Champions League paradox. Imagine feeding your system this query. Where was the 2019/2020 Champions League final held and who won the match? Now look at what happens with a standard, naive text splitter. In the first document, it blindly cuts the text exactly where it mentions the location. Lisbon. Boom. Cut off. But the critical information about the actual winner, Bayern Munich, gets completely isolated over in the second chunk. The heuristic splitter has just completely fragmented these beautifully connected atomic facts. We call this specific failure mode semantic fragmentation. It happens when standard token splitters blindly divide interconnected facts across separate chunks and documents, heavily degrading the cohesive context. And here's the real kicker. This makes it mathematically impossible for a standard retriever to pass high-signal context to the LLM in a single shot. Instead, you're forced to retrieve excess noise, inflating your context window with filler that totally dilutes the signal. Moving right along to section 3, token-level intersection over union math. Let's get into the numbers. To actually solve this fragmentation problem, we have to completely overhaul our evaluation math. We need to establish a framework that actively guards against context dilution. We do this by defining two critical sets of variables. First, TE, which represents the set of gold standard target tokens, the absolute, perfect, exact facts we need. And second, TR, which represents the returned or retrieved tokens, basically everything our system actually yanks out of the database. Now let's step through the actual intersection over union formula, or IOU. Step 1, you find the overlap, or intersection between the gold standard and retrieved tokens. Step 2, sum up the total tokens. Step 3, subtract the overlap to find the union. And step 4, divide that overlap by the union to get your IOU score. So what's the big deal here? Well, this mathematically balances completeness while heavily penalizing noise. Think about it. If you retrieve 1,024 tokens of absolute clutter just to answer a 10-token question, your IOU score absolutely tanks. It's a brilliant guardrail against bloat. Okay, section 4, the chunker model performance matrix. Let's look at some real-world benchmarking. Armed with this new IOU metric, researchers ran a massive benchmark. We're talking 2,520 retrieval runs across 90 different chunker model configurations. And the resulting distribution of IOU scores reveals something super interesting. Sentence-based splitting consistently outperforms alternative heuristics, like pure token splitting. By keeping natural discourse boundaries completely intact, the system maintains semantic coherence so much better than just using a rigid, arbitrary token cutoff. The hard data actually crowns a very specific setup as the undisputed champion here. The ultimate sweet spot, A sentence splitter using a 512 token window with a 200 token overlap. This configuration maxes out at a top performance of roughly 0.099 token level IOU. To put that in perspective, a mid-tier alternative like a token text splitter with a 1024 token window and zero overlap maxes out around 0.093. So moderate chuck sizes combined with sentence awareness is a total game changer.
Next up, Section 5, Domain-Dependent Variations. We're comparing finance versus astrophysics.
Now, before you just go and blindly apply that 512 token window to absolutely everything, you have to realize that the underlying document structure of your specific knowledge domain drastically alters these optimal results. Take the finance domain versus astrophysics. Financial filings are highly structured environments. They have predictable schemas, rigid tables, and explicit numeric lists. Astrophysics texts, on the other hand, are full of free-form narrative academic prose with facts scattered all over the place. Thanks to that predictable structure and those rigid tables we just talked about, finance chunks actually survive boundaries pretty well. Because of this, finance consistently achieves the highest IOU scores across the board, ranging from about 0.06 to 0.11.
But, and this is crucial, if you deploy those exact same chunkers on astrophysics texts, performance literally plummets to a mere 0.03 to 0.04 IOU. It consistently lags behind. When atomic facts are buried in sprawling narrative prose, finding them becomes a true needle-in-a-haystack semantic challenge. It really highlights why adopting a totally domain-blind architecture is a huge mistake.
Finally, Section 6, Throughput, Model Size, and Cost Optimization. For our final section, let's quantify the computational footprint of these embedding models to help optimize your engineering costs. If you plot the mean IOU score against the average embedding time, a very clear good and fast zone emerges. This proves that you don't always need a massive, multi-billion parameter embedder. Smaller models, like Almany-LN or text embedding 3 small, actually deliver exceptional accuracy at a tiny fraction of the computational cost. Which brings us to a massively practical takeaway. Before you go and write a huge check for commercial APIs, the experts advise running a 30-minute pilot using open source scripts entirely in-house. To put that into perspective, you can embed 50,000 chunks on a single standard RTX 4090 GPU. Doing this allows you to benchmark your own domain's optimal chunking strategy before committing your budget. So we've walked through the mathematical flaws of top K accuracy, all the way to finding the 512 token sweet spot that eliminates semantic fragmentation. With this blueprint in your hands, the only real question left is, are you going to keep paying for LLM context noise, or is it time to implement token-level IOU evaluation today? How quickly can you upgrade your RAG pipeline?